Thank you for the kind introduction, Barak, and it's really my pleasure and my honor to be here with Mrs. Bekenstein present to give this. Am I on? No, I'm not on. Okay. To give this memorial lecture to what I consider a really great physicist. So, stand where I can see it here. So I'm going to talk about a formula that Jacob Bekenstein wrote down in 1972. At least he had these 5 terms. This 4 here was added a few years later by Hawking. And when I now teach a seminar course to freshmen in the humanities at Harvard, and I teach them about 3 equations. I think it's important to understand equations. And I teach them about 3 equations: the Schrodinger equation, which describes quantum mechanics, the Einstein equation, which describes general relativity, and the Bekenstein-Hawking area law, and we don't know what it describes. We're sure it's right, but we don't know what it describes, which I think makes it by far the most interesting of the 3 equations. And I and many others, since Bekenstein's work in 1972, have devoted our lives to understanding this equation. And I think it's fair to say that when we fully understand this equation, that we will have a transformation in our understanding of the universe around us, at least as profound as what occurred when we understood the Schrodinger equation and the Einstein equation. We may be some way from that now, but I think we can see it coming. And the reason for that is if you look at this equation, it involves essentially all the main areas of modern physics. It unites thermodynamics, it's got Boltzmann's constant, relativity, the speed of light, it's got curved geometry, the area, it's got Newton's constant, it involves gravity, it's got quantum mechanics, involves h-bar. On the left is the entropy, the so-called Bekenstein-Hawking entropy, and there's a 4 there, so there's mathematics involved. But that's important. It's not a squiggly relationship. It's a very sharp relationship. And so it's a real concrete challenge to try to understand this equation. And what this equation means is that if you have a black hole, it is associated with an entropy. And for those of you, I know there's a number who are not physicists in the audience, the first few transparencies will be at a more general level. A little later, I'll go sort of more to a physics colloquium level. But you can think of this as the number of bits of information, like computer bits, inside a black hole. So the number of bits that a black hole carries is proportional to its area times all the basic fundamental constants of nature are involved in this relation. So clearly it's a very interesting and central relationship. It's a wonderful thing that we don't understand it, because it keeps our salaries coming trying to understand it. And even better, we have many concrete approaches to study it, and I think I can unequivocally state that we understand much more about what this formula means than we did when it was written down 40 years ago. Now, Boltzmann wrote on his tombstone a formula that said that whenever you have an entropy, you should associate with it some number of bits. And that formula tells us how many bits to associate. And it's a very, very, very large number. For Sagittarius A star, which is the supermassive black hole in the center of our galaxy, this number is 10 to the 80. Another way of thinking how big it is if you took all the information in the Google data banks, it would fit into a black hole which was 10 to the minus 24 millimeters across. Now, Bekenstein argued that, in fact, there was a universal bound and that black holes were the best, the most amount of information that you could fit inside an area of the size of the black hole. And that makes them, not just as that this was a law of physics, and that makes them the most complex possible objects in the physical universe. And I think there's a general sense that this basic idea of Bekenstein was correct, though we haven't proven it. Now, there's something called Moore's law, which says, I think it's the amount of bits you can fit on a computer chip it doubles every 3 years. And what Bekenstein said is trouble for Moore's law. In 3 years, if they keep having more and more in 300 years, if they keep having more and more technological improvements, eventually they'll reach the black hole bound, and the black holes will be the best possible information storage devices that the basic laws of physics allow, but we've got quite a ways to go. So this is the first example of the idea that this entropy, the area bounds the amount of information you can fit inside it, was the first hint of what we now call the holographic principle, which is a very general property of space-time. On the other hand, black holes were discovered 100 years ago this year, actually. The paper was published. It's the centennial in 1916. And they were discovered as solutions of the Einstein equation. And according to the Einstein equation, the description given by Schwarzschild and Kerr and others, a black hole in Einstein's theory, space is curved, and there's nothing inside a black hole. And they are, in fact, very simple, bald objects. And this statement was quantified in a long series of mathematical theorems, actually, which we will argue later had a conceptual flaw in them, but they exist as mathematical theorems, and they're the so-called no-hair theorems, that there aren't lots of varieties of black holes. They're all the same. They don't carry any information. They don't have any structure. So we have here a real conundrum. Einstein and Schwarzschild, a really deep puzzle, which takes another sharper form I'll describe later on. But how can it be that something so simple and bald, subject to the no-hair theorem along the lines that Einstein and Schwarzschild described black holes, can also at the same time be the most, not just very complicated, but the most complex conceivable objects in the universe. So there's a real dichotomous nature to black holes. How is it possible that they can store so much information in a hole of nothingness? And this is one version of what's called the black hole information puzzle. And it's solving this black hole information puzzle, which takes a number of different forms, that has occupied the lifetimes of legions of theoretical physicists. Now, some insight into this, which Barak alluded to, and I'm not going to talk about very much, came out of string theory in 1996, in which we looked at some special string theoretic black holes, and we found, and in string theory, the equations are more precise, and we have them under a lot of control, and it is a theory which includes both quantum mechanics and gravity. We found that they were able to pull off this trick of being maximally simple and maximally complex at the same time. And the way this worked was there were two different descriptions of the same thing. A highly more sophisticated version of saying that this glass of water is half empty and half full, two descriptions of the same thing that sound a little different. These two descriptions, it takes a lot of mathematics to see that they're the same. But what happens is there's a lower dimensional holographic information plate that carries something called a two-dimensional conformal field theory that stores all the information. And if we describe it that way, only the boundary of the black hole exists. And we can see the information moving around there, and it can be stored there. It doesn't get lost. And on the other hand, we can map that explicitly to the Einstein-Schwarzschild description and demonstrate their consistency. So this is certainly progress, but we don't know now, and we're not likely to know for some time how and if and in what form string theory is related to the real world. So this is not a solution of the problem. However, it's quite possible, and there have been a number of indications, which I won't review, that it is the case that the trick employed before string theory, we didn't see how it could even be possible that something could be maximally simple and maximally complex at the same time. And so what we've been trying to do is to use the trick employed by string theory and see if it occurs in the real world, in the black holes that we see up in the sky, and without assuming string theory. And this lecture will report some progress in this direction, but the progress was inspired by something which came from a completely different direction and turned out to have applications. And so I'm going to spend more than half the lecture describing what this seemingly unrelated development was. And then at the end, I'll come back and see how it forces us to completely rethink how we view black hole information. So what has happened over the last 3 years is we've discovered that there's a kind of triangular relationship between three subjects, an exact mathematical equivalence between three subjects, each of which has been studied for half a century. And understanding that they were equivalent not only elucidated each of the individual corners here, but it led us on to discover some new things. And the three things are some basic behavior in quantum field theory, the study of scattering amplitudes of particles, as one does at the LHC or at other kinds of colliders. Something else called asymptotic symmetries. These are symmetries of space-times and associated conservation law. And finally, something called gravitational memory, which there are proposals to measure going back to 1974. And with the recent spectacular advances in measuring gravitational waves of the last month or the last 6 months have actually led to new optimism that the gravitational memory effect might be experimentally observed. Okay, so I'm going to start someplace that is freshman or even high school physics. And my first goal is to show that ordinary Maxwell electromagnetism, classical or quantum, we're used to thinking of that as having one conservation law, but in fact, it has an infinite number of conservation laws. So here's a picture of an electric charge which has a radial electric field, and this obeys a static electric charge. It obeys the standard Coulomb law. The strength of the electric field grows off like 1 of the square of the distance to the charge. Now, if you boost this formula, it's all Lorentz invariant. if you boost in this formula, you find that the radial electric field takes this formula. This can be found in Jackson or any other textbook. In electromagnetism, this formula is well over 100 years old. Now, what I didn't understand about this formula until recently is that it is not single-valued as you go very far away from the electron in a spatial distance. And we need, it's going to be important in the following to understand this carefully. So I'm drawing here a picture of Minkowski space, and here is the charged particle. It goes from past time-like infinity to future time-like infinity. And here, I've drawn a diagram in which light rays go at 90 degrees, at 45 degrees from the horizontal. And so this is the place that light rays go to. It's called future null infinity. Let me just call it the future. And there's also past null infinity, the place where light rays come from. Now, the statement is that if you take the radial component of the electric field and you fix the retarded time, which means you go to future null infinity, and you go backwards to this place, which I'm going to call the past of the future. And the important thing to keep track of here, very important subtlety, the past of the future is not the same thing as the future of the past. And they're just not. So if you go to the past of the future, here's the formula. It's 2 lines of algebra to what the radial component of the electric field approaches. If you go to the past and then go up to the future, here's what you get for the radial component of the electric field. So the electric field at the past of the future is not the same as it is at the future of the past. Strangely, if you go to the future of the past, it's the same as it is at the opposite side of the sphere at infinity at the past of the future. So this is true. So there's a general boundary condition, a rather funny boundary condition, that the radial component of the electric field, and this rule comes, in some sense, it was known 150 years ago, that there's a boundary condition that the electric field at the future of the past is antipodally related to the electric field at the past of the future. Now, I showed this for one particle. It's true for any number of particles. With more work, it's implicit in quantum electrodynamics. In the diagrams, the so-called Feynman diagrams that we use, have this boundary condition implicit in them. So this boundary condition is implicit in everything that we do in classical and quantum electrodynamics. Now, it immediately implies that if we take the future, the past of the future, and take any function on the sphere and integrate it over the sphere, the radial component of the electric field, that will be equal to the same thing evaluated at the future of the past, where this function, arbitrary function epsilon on the sphere, is any function which is antipodally identified in this way. Now, if we take the special case where epsilon is a constant, and we use Gauss's law, this implies a conservation law which we're all familiar with. In any scattering process, the sum of the incoming charges is equal to the sum of the outgoing charges. It's the whole sum which has to be equal. That's called charge conservation. It stands alongside energy conservation and momentum conservation as one of the fundamental conservation laws of physics. But now what I'm telling you is that there are an infinite number of conservation laws which are all on the same footing as these 4 basic conservation laws we're familiar with. So let's look at what they are. Well, this first term, you take all the incoming charges. So it's a conservation law for every function epsilon on the sphere. So you take all the incoming charges and you weight them by the angle on the sphere. And you add to that another term, which is kind of an odd duck. You don't usually see it in conservation laws of this type. And it's equal, an incoming odd duck. And it's equal to the outgoing transformation laws weighted by an arbitrary function of the sphere times the outgoing odd duck. What is this odd duck? Well, it involves the electromagnetic field itself, not just the matter charges. And it's linear in the electromagnetic field. And it's integrated over all time without any e to the I omega v. So it's at 0 frequency. That means that it's what we call a zero energy photon or a soft photon. Now, soft photons are discussed ad nauseum in quantum field theory. I don't want to say it's not boring, but they're very important in quantum field theory. At every collision of the LHC, there are literally infinite numbers of soft photons produced. It's very important to keep track of them, and they play a crucial role in this conservation law. And soft here means 0 energy. That's how the term has been used for the last several decades. So this conservation law equates the sum of some kind of zero mode, some moment of the electromagnetic field coming in. So you take the charge-weighted incoming, some angularly weighted incoming charges, you add to them some moment of the electromagnetic field, and that's a prediction, which is an exact conservation law of nature about what you will see in the far future as to what comes out. Now, that was all classical, but what about the quantum world? Well, in the quantum world, what we say is we have an S matrix and we have some incoming state. We act on it with the scattering matrix, and that gives us the outgoing state. And of course, there are textbooks, many textbooks devoted to how, it depends on the particular theory, how you compute this S matrix. Now, but whatever that S matrix is, we have just argued that there had better be a conservation law, and that means that there's an operator Q which commutes with the S matrix, and in fact an infinite number of them, one for every epsilon, and one for and for any pair of in-states and out-states. And in this formula, the strange duck creates and annihilates soft photons. So the general form of this conservation law looks rather bizarre. You take some S matrix element between out and in, you add to it one soft photon, and that's equal to something else acting on the same S matrix element without a soft photon. Now, it would seem incredible that nearly 100 years after the discovery of quantum electrodynamics, we would have discovered some new infinite number of conservation laws. And of course, we haven't. These conservation laws were discovered in a wildly different language, in the language of Feynman diagrams, by Francis Lowe, or maybe even Bloch and Nordzig somewhat earlier, and in the modern form by Steve Weinberg in 1965, and they're called the soft photon theorem. Now, we've set things up in a different way. We've approached it from the view of symmetries, and it takes 10 pages to do the algebra to show that this relationship here is the same relationship that Weinberg wrote down, but it had to work, and it did work. And we could have reversed the logic. We could have started with the soft photon theorem and derived the symmetries. Now, whenever we have we derive the conservation laws. Whenever we have conservation laws, we have symmetries. And so we can take these charges and we can just ask, what are the transformations that they generate by quantum commutators? And they generate large gauge transformations. That is, if you compute it with the gauge field at the boundary at infinity, they transform them by a gauge transformation, which is precisely the same as the epsilon, which appears in the respective charge. And these things act non-trivial on physical states. The effect of the gauge transfer can be measured by what's called the electromagnetic memory effect, which is an electromagnetic analog of the gravitational memory effect, which there have been experiments proposed to measure. So these, even though they're gauge symmetries, because they're big, they have a non-trivial action on the physical states. Okay, now, usually, how is it that this had been missed for so many years? And it's because in most textbooks, one simply demands that the gauge transformations go to 0 at infinity, and so these things weren't noticed. Now, all of this has a profound consequence for how we think about the structure of the vacuum in all theories with electromagnetism. And there will be analogous statements for gravity. So what is the vacuum state? Well, the vacuum state is a state which is annihilated by the Hamiltonian. It has 0 energy. On the other hand, the Hamiltonian commutes with all these charges. That's another way of saying that they're conserved. So if we act on the vacuum with one of these charges, we get another state which is annihilated by the Hamiltonian. It's clearly a different state. In fact, it has different angular momentum. It has an extra photon, an extra soft 0 energy photon. And so that means that there's an infinite degeneracy of vacuum states in ordinary quantum electrodynamics, and they have different angular momentum, and they can be thought of as differing either by these large gauge transformations, or we can just think of them as differing by the addition of different numbers of soft photon. So we could paraphrase this by saying that the vacuum in quantum electrodynamics, far from being a unique, flat, featureless, empty thing, is characterized by soft hair. Now, the fact this is a symmetry generator, and the fact that Q doesn't annihilate the vacuum, we use the words that it's spontaneously broken, and the particle that you create when you spontaneously break a symmetry is called the Goldstone boson. So the soft photons are the Goldstone bosons of the spontaneous symmetry breaking of the vacuum in electrodynamics. Now, there's actually an analogous story for gravity, and oddly enough, usually electromagnetism is simpler for gravity, but for odd reasons, the gravity story was actually understood first, and we went back and said, wait, well, why isn't this also true in quantum electrodynamics? And it is. This symmetry that I'm talking about, the infinite dimensional symmetry, was first discussed in 1962 by Bondi, Metzner, and Sachs, and the conservation laws were 1965, and the associated memory effect was in 1974. But I won't go through the whole gravity story, because it's really just very similar to the electromagnetism
magnetism story, but there's just a lot more indices floating around, so it takes longer to follow. Okay. So now I want to talk about the black hole information paradox. And what is the black hole information paradox? So it's closely related to this, or it's another version of the information puzzle about how, that I talked about earlier, about how black holes store information. So the idea is this. Suppose you take a bunch of massive matter, a star, some PhD students carrying their theses, whatever, and you throw them in and you make a big black hole. And let's also assume, for the sake of argument, that there's actually information in the PhD thesis, often the case. And moreover, that information hasn't been shared with anybody. And we make this black hole, and then according to the laws of black hole dynamics, as they were formulated, you know, from the period of kind of 1940 to the mid-70s, what will happen if you put enough of these together? They will form a black hole with no hair on it, and that black hole, from the outside, there will be no imprint of what went in to make the black hole. That is, there will be no hair on the black hole. And then, according to Hawking, the black hole will very, very slowly radiate. And according to the calculation, the radiation has no information in it. The radiation can be thought of as boiling off from the region outside the black hole. And we should think of this in this picture as the black hole as kind of being a hole in empty space that gets shrunk down to a point and eventually evaporates to nothing. And the problem with this picture is that based on some really very general assumptions, this implies that it is impossible to regain the information, the crucial information, in the PhD thesis in the far future. Now, this is different from throwing the thesis into the fire. If you throw the thesis into the fire, in principle, we believe that if you had perfect information about the laws of physics, you collected every wisp of smoke, every photon, every piece of ash that came out of the fire, you could take it all, you could run the movie backwards, and you could reconstruct the PhD thesis and read it. Not in practice, of course, but in principle. And it's very important that we could do this in principle, because if we can't do this in principle, it means that we don't have laws of physics, right? The whole department, the whole enterprise for the last thousands of years has been based on the idea that we actually have laws and that the universe is described by laws that tell you, given perfect knowledge of the present, perfect knowledge of the laws, you can both predict the future and retrodict the past. Now, that might be true. It might be true that we don't have such laws. The history of physics is, of course, the history of us learning that things we were sure were true, like the sun goes around the earth, in fact, are not true. But none of us thinks that now is the moment when we're giving up on laws of physics. At least I don't. So this is a rather serious charge. And when this proposal was made that universe doesn't have laws, it sounded kind of plausible because the argument was so simple, and many people were persuaded by it. But as the years have gone by, you can't just throw your hands up and say there's no laws. You have to have something else. And nobody has proposed what the something else might be. And there's a pretty general sentiment, though no proof, that this argument is somehow wrong. So the question is, what's wrong with the argument? And people have worked it backwards, saying, what must be wrong in order for this conclusion to be invalid? Which of our assumptions must be wrong? You could try to find an error in the reasoning. That's been done. There's endless literature on this, but I think it's fair to say there's no universal consensus on some reasoning that was wrong. You could try to work this backwards and come up with some which of the assumptions that go into this you could doubt. But the exciting thing that has just happened as a result of this previous work is that we now have good reason to doubt, coming from somewhere else, not from trying to solve this problem, that some of the assumptions that went into this were wrong. The first is that black holes have no hair. So we've shown that there are infinitely many conserved charges in nature. It was always believed that black hole, though there was no sort of proof of this, it was always believed that somehow or another black hole evaporation conserved energy. That whenever radiation went out, the black hole reacted in some way and kept energy as one of its quantum numbers in such a way that the total energy of the system was conserved exactly, not just on the average. So it had energy hair, but energy is on equal footing with all the infinitely other conserved charges, and they are getting radiated off. So part of those charges must remain on the black hole. Finally, the vacuum is infinitely degenerate. So when the black hole is gone, there are an infinite number of possibilities as to what the final state may be. And it's certainly possible that, the final state of the vacuum could be correlated with the outgoing Hawking radiation in such a way that the information is completely preserved. So now we have some good reason to doubt the argument that information is destroyed in black holes. Now, I'm saying this here because we have, excuse me, I want to make it completely clear, since we keep saying it and it has often been suggested otherwise, we have found a flaw in the assumptions underlying the information loss argument. Not the first time anyone's found a flaw, but most of the flaws that have been found have quickly proved to be inessential. We certainly have not resolved the information paradox, but we have found a new way of thinking about it, which might lead us somewhere interesting. So what we would like to do now, and this is work that is ongoing, and the first paper in a series appeared last January with Hawking and Perry, we're trying to understand what this hair is we've inferred must exist on black holes in order for all these infinite number of conservation laws to be valid. Now, the charge itself, these infinite charges, are defined by surface integrals out here, just like electric charge. You define it as a radial component of the electric field at infinity, but now we can weight it by functions and get infinitely many conserved quantities. And not just for electric charge, but for a whole handful or two of other kinds of charges of this general type, including super translations, which I haven't discussed here. So this charge must be conserved, and so its value in the past, if we take this surface integral, we can write it as a volume integral using Gauss's law and the constraint equations in the far past and get the incoming charge, and that must equal the outgoing charge. And now, if there's a black hole here, we have to use Gauss's law. We need a closed surface. We need an extra surface that goes over the black hole. And I should have first said what I'm drawing here. So we start out with empty flat space here. We throw in a collapsing shell of matter. We make it massive enough so that it forms a black hole, which is this region here. The blue is the event horizon. Light rays in this picture can't go more than 45 degrees. So anything that is in here is doomed to hit this singularity in the space-time curvature. And so this region is called the interior of the black hole. This is future null infinity, where light rays that don't cross the event horizon escape to, but some of them do cross the event horizon and they go into the black hole. So if we want to make our closed surface, we can't just close it here because the black hole is in the way. We have to have a piece which we can take to go along the event horizon of the black hole. And if you analyze this problem, you find that just as there were soft gravitons here that represented a vacuum degeneracy that carried no energy, there are soft photons. There are soft photons here on the horizon that represent a hidden degeneracy of the black hole. And these ones here can be represented as boundary terms at the boundary, since there's zero momentum, at the boundaries of Scry, of null infinity. And these can be represented as terms at the boundary here. So here we're seeing a reappearance of the holographic phenomena that we encountered in string theory, which in string theory we know ended up to be the complete solution of the problem of information storage for black holes. But we haven't found everything. We've found one pixel. And so now one would want to ask the question, so I want to call this soft hair on black holes, because there's just like the soft hair which characterizes the vacuum out here. And one question you might want to ask is, can this be measured? Is this a measurable property of the black hole? And the answer is yes. If we consider a process like this, so what am I drawing here? Here I'm making a black hole, but here I'm allowing quantum effects to turn on, and the black hole forms, it gets really big, but then these little red arrows means it's evaporated, and in the far future, one has nothing. Again, we have an exact conservation law, which means if I take this conserved charge out here at the bottom of, at the past of the future, I can take it and evaluate it over a surface like this. If I do this, I find that it makes a soft graviton on the horizon. And I can compare that to what I get. It must be equal by the conservation law. I can find what it does to the outgoing state. And so I can get an exact relation, not a probabilistic relation, between the difference in the outgoing state of a black hole with one soft photon and one without soft photon. That is something which violates the basic tenet, the basic conclusion of Hawking's argument, and the basic tenet of the no-hair theorem, that all black holes are the same and that we can't, except for their mass and their angular momentum, and that we can't get any deterministic predictions about the difference between different black holes. So that brings me to the end. And my concluding comment is that black holes carry quantum hair in the form of soft gravitons or photons arising from these large gauge transformations or super translations. These are some of the pixels in the sought-after hologram at the boundary of the horizon. Now, you might ask if these pixels account for all the information. That is, you might ask if we can explain this. You might ask if we can explain this fundamental formula here. You might ask if we can find this 4 and fully understand this problem. And that was something we did manage to do in string theory. But for various reasons, we think, which maybe I won't go into, but for various reasons, we think it's not likely that what I've told you today accounts for all the pixels. We want to have HD. So far, we don't even have whatever it is they used to have. We're not even to 430K, I don't think. All right. But we found a few pixels, and that's very encouraging because we used to think there were no pixels. We didn't know how to describe any pixels. And not only can we describe a few pixels, but we have very concrete ideas about where to look for more. There's something really interesting that people have discovered in the last 10 years called superrotations, which are more symmetries of black holes, but there's a lot of things that we don't understand about them. And so whether or not we can complete Jacob's program of finding the complete story of how it is that black holes manage to carry so much information is an open and interesting challenge for future research. But I hope I've persuaded you that Jacob has continued to bother us to this very day, and that his legacy of trying to understand these very important problems remains alive, well, and thriving.
Okay, we want your questions, both from enthusiasts and from professionals. Yes.
Don't you think that quantum mechanics is already not deterministic by the measurement process that I can't know what the state was before I measured some state because it collapsed?
No. No. My view on quantum mechanics, this is a subtle question on which there are many volumes written. And my view on quantum mechanics is that when we went from classical mechanics in classical mechanics, we were instructed to measure positions and velocities. And Newton and many others attempted to write down deterministic laws that tell us, given initial positions and velocities of anything and all their interactions, we would be able to exactly determine their final positions and velocities. My view is that the fundamental meaning of the transition from classical mechanics to quantum mechanics is, first of all, that I guess it was, as Heisenberg said, that in quantum mechanics perhaps was the first time in which our understanding of the physical world transcended the things that we can feel, see, and hear. And the nature of the fundamental entities of the physical world really do not correspond to our physical intuition. That we will be misled if we try to think of the world in terms of what we are used to, and that the fundamental physical reality is the quantum state, from which the things we like to talk about, positions and velocities, can only be approximately determined, and that the physical state itself obeys completely deterministic laws, the Schrödinger equation. So in that sense, the idea of determinism was not altered one iota from the transition from classical to quantum mechanics. That's my view on it. People will argue with me. But even the people who will argue with me will agree there's a problem here. They will just say it in a more complicated way.
Yes.
I've understood that your stance on general relativity, one of the great things about it was that directly Einstein's relativity pointed us at the point where it falls down. The point that you could look at the equation, you could see that the center of a black hole, it just doesn't work. Do you think that there's something similar that we could take from the Bekenstein equation?
I think it's even more true of the Bekenstein equation than the Einstein equation. And, you know, this is progress in science. Every equation that everybody has ever written down is wrong and ultimately gets replaced by something better. So Newton's equations were replaced by Einstein's equations. Classical electrodynamics was replaced by quantum electrodynamics. That's what we hope for. Even the great physicists don't hope that their equations will be eternal and never be modified. Everything gets modified. Now, the really peculiar thing about the Einstein equations, which I'm not sure ever really happened before in the history of physics, is that they predicted they were going to fail. You know, the Maxwell equations are a completely self-consistent set of equations. They don't predict that they're going to fail. We do measurements and we know that we need to incorporate quantum effects, the black body radius, and so on. we measured that they were wrong. And Newton's equations of gravity don't predict that they're going to fail. Now, Einstein's equations predicted that they were going to fail in the black hole. So it's not a bad thing that the theory predicts under certain circumstances that they'll fail. In fact, it's a big disappointment to all of us that they only seem to fail inside a black hole where we can't see them and we can't measure what the thing that will replace Einstein's equations will be. But the modern point of view is that Einstein's equations surely receive corrections. And those corrections, we can write down explicitly what they must look like. And those corrections will become big long before we reach the singularity of the black hole. And there's no reason to trust the Schwarzschild solution that predicts the singularity in the region where the singularity occurs. So people shouldn't have been bothered by that. They should have been happy about it. What they should have been bothered by is that the singularities do us this great favor of breaking down, predicting their own demise, and then hiding it when they do it.
Yes.
Maybe a related question associated with the fact that Bekenstein basically discovered an intrinsic coarse graining coming out of the interaction of gravity and quantum mechanics. And that seems to relate to other questions of issues of what's called space-time fold. Finite size effects ultimately coming from plane scaling. Can you comment on possible connections or discretization of space-time coming from the fact that if you go too small, fluctuations become too highly energetic?
Yeah. So if we accept the uncertainty principle and of quantum mechanics, and we accept Einstein's thesis that in general relativity and in the universe around us, space and time are themselves the things. In electromagnetism, the electromagnetic field carries the energy and is the actor in the dynamics of electromagnetism. In general relativity, the actor in the dynamics is space and time itself. Space and time itself are wiggling around. And that has been dramatically and wonderfully confirmed in just the last month in the detection of gravitational waves from the black hole merger, where we saw that in Hanford, Washington, and in Livingston, Louisiana, space and time were stretching and twisting and doing exactly what Einstein predicted. That space and time are not flat things. And we've known from, of course, from the perihelion measurement and from bending of light in the sun, that space and time could be curved and static. But now we've seen that there's ripples in it. Now, if it's ripples and it moves and it carries energy, it better be subject to the uncertainty principle. And now you can do a very simple back-of-the-envelope calculation. So the uncertainty principle is a small effect in everyday circumstances. The amount that my head is wobbling around because of the uncertainty principle is incredibly small. Nobody can see it. And but a very simple calculation, which all physicists will agree on, that if you look at space under a very, very powerful microscope, 10 to the minus 33 centimeters, that the ripples in the geometry in space and time will become as big as the geometry itself, so much so that the very notion of geometry becomes meaningless. So we know, I think it is generally accepted by all practitioners of modern field theory, quantum, that at that scale, that if we had microscopes of 10 to the minus 33 centimeters, which of course we don't, but that if we did, we would see space and time itself dissolving. And that, what happens next, is exactly where the agreement ends. We don't know what happens then. We don't know if space is discrete. We don't know if there's strings. We don't know if there are loops. And this problem may well be tied, the extent to which it's tied to the problem I've been discussing is also an open question. But we don't know that space is discrete. That's a hypothesis.
One next question, please.
So slightly more technical, you suggested that your identification of charges associated with soft gravitons can explain part of the entropy associated with the black hole. But a single soft graviton mode is a Bose degree of freedom, in which in principle I can in fact encode infinitely large amount of information. So as long as it's a Bose degree of freedom, haven't you gone from being puzzled over zero entropy to the opposite extreme of having a way of encoding infinitely much information, which is also not the hoped-for answer?
Yes, that is certainly an issue. And the other end of the issue also, of course, is the ultraviolet cutoff. Why I can't have long wavelength but small. The soft gravitons can be small. They can tile the horizon a priori at a smaller scale than the Planck length. I don't know the answer to that problem. And I expect it has something to do with how many of them you can excite when you make a black hole. That's really all I can say. But the basic answer is I don't know.